So anyway, as you probably guys know, I am leaving HP. It's my last week. And I love talking. I love talking about code, so I thought I'd give one last presentation on some of the code and some of the things that kind of have been in my brain lately, and I think that I kind of wanted to just talk about. And the thing that I've been thinking about lately is combinators. I'll talk more about what they are. But I just wanted to prepare you because this talk is going to be a little rambling because I'm going to kind of start philosophically and talk very generally and high level, and I'll kind of narrow down and kind of get to the actual point of the talk. So be prepared for some general stuff. So the first thing that I want to talk about is when we write code, when we write software, we strive for a couple of things. One of those things is flexibility. When we write code, we want to make sure that code can adapt to the future situations and to kind of new requirements that come along. So we don't want code that can't be reused, that can't support change well. So flexibility is a key thing that we need in our code. The other primary thing that we kind of search for in code is clarity. Right? When we write code, it has to be passed on to other people. So you need to be able to write code that can be understood by other people. So maintenance and understandability are primary things. Now, most of the time, well, some of the time, these things go hand in hand. Let's see. And now I'm going to use it. Batman versus Superman. Some of you probably will see that movie at some point.
Not yet.
Maybe in 10 years. Anyway, so most of the time, Batman and Superman work together, right? Flexibility and clarity go hand in hand. You write a piece of code, you factor out a function that can be reused. It becomes more clear, and it becomes more flexible. But sometimes they fight. Sometimes when you make your code more flexible, you actually decrease clarity. And I'm going to use control point as an example because I like using control point as an example for things. Control point, you can control the number of tabs in the UI by changing database lines, which is very powerful, and the argument for it is, it's very flexible, but it really decreases the clarity. And so one thing that you kind of need to think about when you write code is this balance, right? And then the balance, more pictures of Batman and Superman fighting. And the balance is difficult to do. And there's a couple reasons for that. And they have to do with human psychology. One is that when we understand something, so we think it's clear, right? We see things from our own perspective. So oftentimes we don't value clarity enough. And the other thing is in terms of flexibility, we try and imagine a magical future. We predict things, and we really think we're good at predicting the future when we're really pretty stupid. So that makes us value flexibility a lot more than we should. So I just want to kind of bring these up because these are kind of balancing factors in how you approach code. And because this situation of flexibility versus clarity will probably come up a lot more in your career than Batman versus Superman. Although that may come up in your career as well. So, I mean, you can kind of do a little thought experiment, like when you create a feature, like what is the cost in clarity versus the value in flexibility? And you kind of need to think about how those things balance. So again, I said I'm going to kind of wander around and talk about different things before I kind of focus on what I want to actually talk about. So now I want to talk about language and vocabulary. So we talk a lot about language, right? We talk about, Java is a language, JavaScript is a language. So I want to use an analogy here with language, and that's vocabulary, right? So if Java and JavaScript and C# and C are languages, what exactly is vocabulary? So kind of the naive answer, the first answer that probably is all in your heads is keywords, right? There are keywords in the function, like the whole system, that kind of are the vocabulary. But when we approach code, there's more than just keyword that is generalized between like two programs. That is more than there's more stuff that's common between two programs than just business logic. Patterns, for example. like using a rest layer. That's kind of, I would characterize that as kind of vocabulary. It's a pattern we use, right? And so I want to talk a little bit more about these patterns. In 1994, the Gang of Four or whatever came out, or the Gang of Five, I don't know, but Gang of Four. They came out with this very famous design pattern books. They said, here's these patterns you can use to develop software. And they're kind of, what you would call tools in your tool belt. There's probably not too many Hanselman fans out there, because there's not a lot of C# people here. But Hanselman is this guy who's like constantly talking about, you need tools in your tool belt. I mean, it's one of his favorite analogies. But design patterns became like basically a tool in your tool belt. But I'm going to also say that they became part of the vocabulary. And that's emphasized in a lot of the way people talk about design patterns, because they talk about design patterns are language that engineers can use between each other. Like, if I say, oh, well, why don't you do it as a singleton? Probably everybody will understand that. If I say, oh, you want to do it as a decorator or an adapter, that's kind of a language we can use. And that's kind of, I think, kind of the vocabulary of code. So now I want to talk a little bit about these patterns. And these patterns are also a little bit dangerous because you have to understand them, right? So if you come onto a project and you don't know these design patterns, and they're scattered all throughout the code, it can be difficult to understand what's going on, right? And the idea here is that I'm trying to express is that vocabulary can be very, very powerful. But when you first come at it, it's just a bunch of gobbledygook, right? If you listen to our conversations in products, we build the vocabulary around a product, GRE, I don't know, CMX. Like we have this vocabulary that we kind of understand. And so once we have that vocabulary, the vocabulary becomes powerful. So the idea is that even if you have patterns that at first kind of seem difficult to understand, like they have a cost and clarity, later on they have value. If the patterns have value, I mean, you can obviously have a pattern that has very little value. But if the patterns do have value, you pay an upfront cost in terms of understanding it to give you more expressive power later. I want to talk about the lambda calculus. This is about sheep. No, lambda calculus is not about sheep. So in the 1930s, before there were really computers, there were a couple guys. One of them was named Alan Turing, and one of them was named Alonzo Church. And they were like massive nerds because they figured out the core foundations of computer science before there were computers. Alan Turing came up with this thing called the Turing machine, which is really just a way of building the simplest possible computer on a piece of tape with ones and zeros on it. So the idea was, that he expressed was, I can compute anything just using a little head that moves along a piece of tape, right? And that ties into how we think about computers, right? A hard disk it's not really tape, but it used to be tape. And kind of that whole notion of you're changing ones and zeros on some sort of, stream of data. That ties into how we think about computer science. But there was another guy named Alonzo Church, and he was even more of a massive nerd than Alan Turing, maybe. I don't know. I'd never met the men. I think they were both long dead before I was born. But anyway, he developed something called the lambda calculus. And the lambda calculus is actually a lot like the Turing machine, because what he was trying to do is build the simplest notation he could to be able to compute anything, right? So Alan Turing, the Turing machine is about a theory of computability, right? Anything that can be computed with the Turing machine. Now Alonzo Church wanted to say anything that can be computed with the lambda calculus. And the lambda calculus is a very simple thing. It's just functions. Just functions being able to take functions and return functions, right? So it's kind of a very mathy, very weird kind of notion of, I can use this weird notation to express basically everything that can be computed. So it was kind of crazy. And the reason we still talk about it today is because of the notion of functions taking functions, right? Otherwise, we wouldn't care about the mad ravings of a mathematician in the 30s. But basically, when people talk about functional programming, they often invoke the lambda calculus. In Java 8, although there's a lot of Java people here, in Java 8, one of the big new features is lambdas, right? The ability to pass functions, right? And so the lambda, and that word comes from Alonzo Church and lambda calculus, which is really just talking about, which really is really just invoked to describe the power of functional programming. So now I'm going to talk a little bit about functional programming. This isn't the core of what I want to talk about, but I think it is important to talk about functional programming. If you want to talk to people if you want to talk about functional programming, there are a lot smarter people than me who have done really good talks on YouTube about functional programming. None on what actually I want to talk about, but I'll get to that soon. Okay, so when people talk about functional programming, they think about a few things. And one of them is no mutations. Can anyone guess what this is from?
Resident Evil.
Ah, you're awesome. Okay, anyway, so one of the key things about functional programming is you have what are called pure functions. And what pure functions means is you pass in your parameter, you pass in your data, and you get back a response. And for any set of data you pass in, you get the exact same response. Also, nothing changes. The function doesn't change any external state. It doesn't do console.log, or it doesn't communicate with the database. It's just you put data in, you put data out. It's always the same. And this is kind of the notion of what a function actually is, because computer scientists, we stole that term, right? We stole that term from mathematicians. And they mean something more like what we mean when we say pure functions, right? Is that for a given input, you get an output determined by that input. So there's no side effects. And there's several reasons why this is really powerful. One is that it's easy to reason about. You look at a function, you know what it's doing, you pass stuff in, you get stuff out. It's very easy to kind of hold in your brain and utilize. But there's a lot of other things that are very useful about it that become increasingly important as we kind of have these powerful VMs that actually run our code for us. One is that if you have pure functions, you can make them run them in parallel, because you know they're not going to change any outside state. The VM, if it knows that if you're running on some sort of virtual machine like the JVM, or the .NET framework, the VM can say, oh, well, I know this is a pure function, so I can change when the execution happens to optimize some internal state. All pure functions can be memoized, and memoizing is a technique where instead of running the function, you just run the function once and pop it into a hash table, and then you never need to run it again. If you remember back to your first year of computer science, you probably did a factorial program. And in your factorial program, it's really inefficient if you do it recursively, because it's constantly refiguring things out. But if you memoize it, you suddenly get this enormous boost in increase, because you don't actually need to figure it out for every input, because you just store it in some sort of hash table. But one of the key ones is testability, right? So let's have a raise of hand. Who really likes Java mocking frameworks? Come on, I know Mike's going to raise his hand. So mocking is hard, and if you go and kind of look at the notions behind test-driven development, there's a lot of, if you read Robert Martin's He's a Craftsman series, where he kind of introduces, he's one of these prime proponents of test-driven development. He introduces prime numbers. Wow, that is a pure function, right? The numbers that are prime are probably not going to change based on the time or some random number, right? Or your database state. So it's a great example of just, I pass things in, I get things out. In the world we write code with lots of side effects that use lots of components. It becomes very difficult to kind of write tests. And we do a lot of mocking and all sorts of stuff to make it easier to do. But if we could try and move our logic into these pure functions, it would make our testing much easier, right? So there's another aspect that people talk a lot about in functional programming, and that's immutability, right? So I'm not going to talk a lot about immutability, because I think that it's a much harder thing to do. But a lot of the languages that are kind of really functional programming languages kind of focus on this immutability. Like once a variable is signed, it can't be changed. Now, a lot of kind of the modern object functional languages, I think like Scala, you can, and Java does this too, actually. You can say this variable will never change, or this variable will change. I think in Java. So that's kind of a powerful notion in terms of for avoiding error, because you have state changes where things get confusing, right? And also it has value for parallel programming, concurrency. Because if no data changes, you don't have to worry about having one thread change a piece of data that you didn't expect to be changed. So also, when we talk about functional programming, we talk about a certain style of programming. This is kind of like, I would call this like first level functional programming. And that's basically the ability to pass functions. And so these keywords are keywords kind of, more standard thing, map, reduce, filter. And the essential idea behind them, is that you have a function, like you have an array, and it has a function called map. And then into that function, you pass a function, and that array will run that function on every element to produce a new array, right? And so you can string these things together and pass in functions, or as Java 8 calls them, lambdas. And you can kind of have this style that's very clear because you know what you're doing. You're filtering, you're mapping, you're doing something. It's a very nice style, and I'm not sure. And Java 8 probably supports it. I don't know a lot about Java 8. But C# has something called link, where it supports this exact style. You can pass in functions. Now, it uses different words, which I think is actually kind of interesting, because the words it uses are select and where, and those kind of words, and which are database words, right? And so if you look at the database, it actually has this style already in it. It's embedded. It's not functional, obviously, but it kind of has this kind of notion of it's kind of built like this already. So a lot of people, when they kind of talk about functional programming, they'll talk about these kind of things, the ability to pass functions to data structures and have the function work on that data structure. So now I'm going to go in a completely different direction. So I wanted to say one thing about functional programming and object-oriented programming. So even though people make a big difference, like there's a lot of things that are different between the two, but they kind of drive off the same concept, and that's encapsulation. Oh, wait, I would promise to use the word cuneiform. That's cuneiform, which is a clay tablet, and they have a little chisel to knock out letters. So anyway, I don't want to go back on the promise to say a word. Anyway, so in functional programming, you have encapsulation around a function, right? You can have as much state as you want inside that function, right? But it all can manipulate, and it can do all sorts of things, but it doesn't leave the function. Well, the object is the same idea. The idea of the object is the object has its own internal state and internal properties, and that state never leaves the object. It just theoretically just pass messages back and forth. One object messages another, and then they manage their own internal state. So that kind of idea drives both functional and object-oriented programming. So they're not, we kind of think of them as different things, but they're unified by kind of these core principles. So I'm going to change directions again because hopefully I'll tie all these things together. Single responsibility, right? So this is a notion that every piece of code or everything should do one thing, right? Only one thing. And that's how you write good code, right? Your functions should do a single thing. And that's really not how we end up doing things. I mean, I think that most people in this room have written code that probably violates this principle. If not a lot, then at least a little. Code tends to do too much stuff. So it helps us to kind of try and find patterns that allow us to kind of break things down far more. And now I'm getting kind of to the meat of what I want to talk about, and that's combinators. This is a picture of Voltron, defender of the universe. Um, it's a little bit of stretch, Combinators Voltron, but he kind of combines 5 lions combined into one giant robot. So I decided to use him as a thing. So anyway, what are combinators? Combinators, there's probably, if you go into the lambda calculus in like the mathy kind of world, there's probably a very specific definition that I will abuse horribly. But I'm going to use kind of a simple definition is that a combinator is a function that takes a function and can possibly return a function. So I'm going to talk mainly about, well, I won't, something called decorative combinators, where I take a function and I pass it to another function. That other function does something, but it really runs the first function I passed to it. And so it does some other stuff. So a lot of times when people talk about combinators, when I go online and I try and learn stuff about functional programming, a lot of it is very general. It's kind of these vague notions that, oh yeah, curry all your functions, and I won't talk about currying, but you can look that up on your own. But it talks about these kind of vague notions, and what I kind of want to talk about is really about trying to make combinators practical. Like, how can you use these in the code you write every day to kind of make your code more powerful and more expressive, right? And so, and I'm sorry to the Java people, because you write Java, and that's a problem for you. And Java has Java 8, wow, it's what, not 100 years, but 90, 85 years after they made the lambda calculus, you found out lambdas, it only took 85 years, and now you can write code like map and reduce and filter, and that is great, and that's a big step. But you can't do some of the things that a more functional language can do. So my examples are now going to be in JavaScript. And my apologies to Java people for the failings of James Gosling or whatever it is. Okay, so this is the identity combinator. And this does something really exciting. It takes a function and then returns a function that does the exact same thing. So you can see that it takes a parameter, and that parameter is fn function. And then it returns a function that takes arguments, and then it generates a return value based on the function that was originally passed in. It runs that function on the context and on the arguments that were passed in to the function. It's hard to explain this, but hopefully if you know some JavaScript, you can kind of understand what this essentially does. But it's really just returning a function that wraps the function you passed in. And it doesn't do anything. It just takes the arguments and passes them down and applies them, right? For JavaScript people, you notice I use the fat arrow notation and the functional notation and the function notation. And the function notation actually is important here. If you change that to a fat arrow, everything will explode. Fire will shoot from the computer. So this is kind of the starting point, I think, to generate combinators. And I put in some comments here, like enclosed. You can capture things in a closure that will be shared by every invocation of the function, right? So you can have state for the function, and all the calls of the function, right? You can do stuff before the function runs. You can do stuff after the function runs. So I'll just press a button. I'm doing logging, right? So this is just a logging combinator, right? So a lot of times we'll have a function, and it will do some stuff, but we'll also want to put logging in there. And that, if you think about it, that kind of violates the single responsibility principle. I mean, don't you just want to have your function do what it's supposed to do? You don't really want it to have to worry about logging. So this is kind of just a general thing you can apply to any function, and it will just log its arguments and its return value, right? And you can put in more stuff here. This is just an example of how you can immediately do very powerful logging, very simple logging. I'm using combinators. Okay, so I also promised to use the words asynchronous decorative combinator. So this one is actually in the CMX code. So basically, this combinator So this is an asynchronous combinator. So it returns a promise. In Java, it would return essentially a future. So they call it, everyone, like Java and C#, and everybody has to have their own names for things, right? So JavaScript calls them promises, and Java has to say, oh, we can't use that. We've got to call them futures, and .NET says, oh, we got to call them tasks. So it's a little confusing, but they're all basically the same idea. So this takes a function that returns a promise, which is kind of an asynchronous thing that happens in the future. And it makes it so that if you call it multiple times, it will only happen once. It will only run that first promise once, right? So, if you have like some sort of submit button, and you're like, oh well, this is kind of a bizarre web problem, but well, if they're banging on that submit button because it's not going fast enough, well, you don't want it to, you don't want that to submit 10 times because maybe they're like buying something and they want to buy one marker and not 10 markers. So this kind of solves that problem, right? And then your code, your buying marker code, can worry about buying a marker and not worry about, oh, well, I need to take care of that special case where this might be called before I've actually finished the call, right? This can take care of that, right? So I think there's a lot of applications for this kind of pattern. Let's do logging, error handling, resource deallocation. Java, like again, the name thing, Java has a mechanism called try, right? So it has something called automatic resource management. So if you encapsulate something in a try block and it implements some interface, then it will dispose of its things. And .NET uses using and iDisposable. But they had to, that was such a common pattern in Java and .NET, and then Java and C#, that they had to build it into the language because people really wanted it. But you can see with this kind of pattern, you can imagine like that the first line. Well, let's go back there. The first line creates an object, right? It passes it to the function. In the second, in the third comment line, I can do stuff here. Then disposes of it. You can also put the try and the catch here. So if you had first-class functions, you would not have those other language patterns because they would be useless, right? They'd just be, you could do it all with combinators. So that's just one example of a problem that they solved with special syntax that people really worked hard on. That if you use something like this, if you use combinators, it would just be a non-issue, right? And there's something called aspect-oriented programming, and I don't know a lot about it, but it's to solve this kind of problem, which is just instantly solved by combinators. Again, caching, memoization, you can make them asynchronous, right? So you have a lot of you have functions that return promises, and you can kind of write combinators around those to do interesting things with those promises. You can have it fail on a timeout, right? Or kind of run only once every X seconds or something like that. There's a lot of applications here. So I mean, the reason I want to talk about it is because I'm excited by it. I think it's an exciting way to write code. Let's see, I wrote an exception handling combinator. Like if you look at your code, you're going to see tons of exception handling. And what that is error handling. So again, you violated your single responsibility principle because you have your code that's doing stuff, and then you have a whole bunch of error handling code. And in some of I made these slides somewhat quick, and it's a little bogus. But you can imagine that you have some sort of exception handler, right? And you have generalized things you want to do with exceptions. If you look at those catch blocks, you're not going to see a lot of variety, right? You might see some logging, and some maybe rethrowing, and maybe some setting some properties to null, but they're not that interesting. So you could kind of write all your code using some sort of exception combinator and never have a try-catch block in your actual written code, right? Your code could just be about your logic and not about, oh, what happens if I have a problem? You can extract that code into the combinators, which is very, very hard to do in kind of a traditional without functions as a first-class object. Okay, and so now I want to talk about TypeScript, right? Because when I first started, people are probably aware I have a love-hate relationship with TypeScript. But in the latest version of TypeScript, they introduced something called decorators, right? And these little @ signs at the top are called decorators. Well, they look a lot like what Java calls annotations, right? And C# calls attributes, right? Everybody, they always have to have their own names. God damn it. So anyway, this is how you apply combinators in TypeScript. You just put the at and then run the combinator and the arguments. I mean, there's a little more stuff that goes on, right? There's a TypeScript identity combinator, which I actually have on my blog. But you can write code like this. And it's actually more powerful than the Java and the C# world. Because in the Java and the C# world, those annotations are read by frameworks, right? It's a way of telling a framework about your code. But this just actually changes the way the code runs, right? So you can write code using these combinators, right? Imagine if you're writing a function, and instead of putting logging and exception handling kind of embedded in the body, you put them at the top, right? And then when you write tests, you don't test those things, right? You test your base combinators and say, you suddenly tested logging for all your functions, right? Or you tested exception handling for all your functions. And then you can just write tests that are specifically about your business logic for your functions. So I think that's a powerful idea. Here's a memoizing combinator. This is a little longer, but basically like you write a function, then anytime you happen to run that function again, if it the value gets stored somewhere. This will only work with pure functions, but I just wanted another example. And that's kind of what I had prepared to talk about. So I just think that this is, programming goes through kind of fads and waves, right? We change the way we program. 40 years ago, people were arguing about, is GoTo valuable? Is there any value in GoTo, right? And kind of over the last, number of years, or the last 10 years, people have started saying, well, functional programming is really good. It's going to be really good at solving certain problems, like, with parallel computation. It's going to make code easier with large systems. So don't ever think of code and the way we write code as something static, as something that doesn't change, right? It's always going to be changing. It's always going to be evolving, because we're going to write better tools, right? And two, the way we write code is going to change because we're human beings and we're subject to fads and in terms of our understanding and changes in the vocabulary, and someone will come up with a great idea. And I think that this is a good idea that is going to catch on, because as functional programming grows, people are going to be able to do more with it. And this is one of the things that I think is going to happen. But again, and also one of the reasons I want to talk about this is if you go online and you look about and you listen to people talk about functional programming, they won't talk about combinators much. They'll talk about the lambdas and passing in things and doing map reduce and that kind of thing. They'll talk about pure functions. They'll talk about immutability much better than I do. But this I think is kind of interesting. I don't know. Hopefully, this was an interesting talk. But that's really all I have to say. So if you want any questions or to talk about anything, feel free to speak to me now, because in a couple days I'll be gone. If you just want to insult me, that's cool.
So you mentioned that the link between, I guess, object-oriented paradigm and functional paradigm is the whole process, or the whole idea of encapsulation, right?
Yeah.
So like in object-oriented programming right now, the way we organize, I guess, our code, we have our classes that focus on doing one thing and trying to do one thing well. But how would you organize code in this functional paradigm? Will you just have, I want to use the word class for lack of a better term, I don't know what it's called, but do you have a class that has all functions that deal with math or?
Yeah, so I don't write pure functional code. But I don't think that we can, because the value of what we do is changing state, right? So if we embrace a paradigm where you never change state, that's going to cause us problems. So my personal opinion on that is that you need to take value from the functional programming, but you probably will have objects that will have some sort of role that they need to do. But what I think is valuable in the approach is trying to break your logic out into pure functions, right? And you'll find it much more testable, right? And then you can write pieces of code that are like, oh, this piece of code does side effects. Oh, I communicate with the database. Now that you've prepared this object for me, I communicate with the database. Or, I communicate with some other external thing. Because you have to have that, right? Otherwise, your code can't really do anything. But if you have a whole bunch of logic, try and separate it out. And I don't think it's always easy, but I think it can be very valuable in terms of how you write code. Because it encapsulates the kind of complexity into more understandable pieces, into more testable pieces, into actually more parallelizable pieces. So is that a reasonable answer?
Yeah.
Okay. Any other comments, questions? Yeah, what's up?
Kind of a tangent, but relates to something you mentioned. You mentioned memoization, like the idea that as you're doing your work, the way I understood it, as you're doing your work, you're saving the results in a hash table, right? So I think maybe could you go through, so we have a problem that this can be a direct application for. It'd be nice, it would be like a vehicle for you to show us a practical example of that. Can I?
Of memoization?
Yeah.
I wrote a memoizing comment. I haven't tested this code. This code I just wrote in 10 minutes to make a slide. But the basic ideas are there. It's like...
We also have it checked in CMX.
Oh, this is also checked in?
You did it.
Oh, yeah. So this is also in the CMX code. I called it simple cacher. But, yeah, you broke it.
It's just not working.
Yeah, no, I think there were some problems with the underlying.
I think we use it for permissions.
So the code isn't complex. I mean, the core of it is right there. It's like just when you compute a function, right? If it's a pure function, then you can take the arguments, convert them to a hash key, and then just store the result, right? And so then whenever you call the function, you need to check that hash key, right? And so normally the way you would do this in kind of a Java or C# language is you'd have that code inside the function. The idea here is that you have the code outside the function.
Okay.
Now, if you are trying to solve that problem, you probably are going to be stuck with writing it inside the function, right?
Yeah, so it's not so much where the code's, this is very nice, but it's not so much where the code sits, it's just, we have it's not exactly a factorial problem. Basically, we have to have an association of one user to multiple groups, and it can be direct association where it's right under the group, or it can be indirect association where the group has a parent group, and so we have to go around. And we are not sure of how many groups the user is associated with, whether there's duplicate associations, but the requirement is that we have to give all the groups that the user is associated with directly and indirectly. So the problem is, one idea was, okay, ahead of time, when we populate the groups in our database, rather than just populating the direct associations, we calculate all the possible indirect associations and put them there. But that makes things extremely complicated because whenever you add a group or whenever you modify anything in that structure, you have to go through all of those and then redo that. And then the other option, which I thought was better, was just you save only the direct associations, but then each time when you ask what are all the groups the user is mapped to, then you have to redo this massive calculations where you recurse to all the groups and figure out all the relationships. But it seems like what you're saying is a great workaround for us where we just save the state in a hash table as we go.
So, the difference is state, right? So that's the problem. So you're dealing with a living data structure that can be changed, right? And that's really your issue. If it was a pure functional thing in terms of sort of calculating something, memoization would be great. In terms of, so memoization kind of becomes caching at that point, where if you have an expensive operation, you store that and you kind of, you say, oh, well, maybe I'll have some sort of mechanism that'll time out my cache. Maybe it's through time, or maybe it's like an update mechanism saying, oh, someone added a user, validate everybody's cache, right? But, so this is kind of a database thing, so there may be more powerful solutions, but it seems like something like a view is kind of what you're going for in terms of a calculated piece of data that's a representation of kind of deeper data.
Yeah, but the view you'd have to, I mean, my understanding is for a view, you would have to recalculate it every time.
Right. So the problem with the view is that you incur an expense when you.
And that's exactly our thing. Like, we don't want to incur that expense. We want to, I guess, the way I understood yours was that rather than redoing the same calculations every time, you save the state somehow in the hash table.
Yeah, I mean, you could. I mean, I don't know the details of the problem, but I mean, you could. One way to approach kind of these large state mechanisms where you have to kind of dig into it is you can save partial answers, right? And then you run into the problem of caching, right? So there's some famous quote about computer science where there's only two difficult problems in computer science: naming things and caching. So caching becomes very difficult. So it's a dangerous world, the world of caching. And memoizing is typically thought of not as caching because you're guaranteed to have a pure function that always returns the same thing. So you have a problem where it sometimes returns something different. So then you have to suddenly manage that cache. And if you break the problem down into smaller pieces, you have to manage all those pieces and how they time out, and how they, whether they're valid or not. So that's a difficult problem.
So memoization is for things like cons, basically things that will never change. And
right.
Just if you need to calculate a factorial, obviously those.
Yeah. So I mean, it's more for things that are pure functions. Now you can apply it to something that you run on a data structure, but you're going to assume that when you're running it and when you're using the memoized values, the data structure isn't changing, right? Like you might do something that goes over a tree, might calculate values for nodes or something. In that case, memoization is good until the tree changes, right? And then the version that I have in CMX is that way. It's like there's a little mechanism you can say, oh wait, all this is invalid, so scratch it all, right? But combinators are more about. I mean, I think we're drifting off from.
Yeah.
So that's okay. Anything else? Well, I hope this was not too arduous.
Will I got it right? Yeah, so it was related to the TypeScript way of how we do it. So when you use combinators with the TypeScript syntax as decorators, so how does it actually, compile to JavaScript? I mean, what does it look like, the final result?
The compile result, I don't remember. I can tell you a little bit about how the combinators work. For a property, for a function or a class or whatever, it basically runs the function that is the combinator on the properties of that class. So you can pull the value of that function name out and modify that value. So, I mean, you can go to TypeScript Playground and kind of try it out to see how it decompiles. But the TypeScript combinator is something that I've tried and it works, and I think we're using it. No, we're not using it. But yeah, so I didn't go into the details of how it works. I mean, I can send out a link that kind of goes into more detail about the identity combinator TypeScript. But yeah, so in Angular, the decorators are used extensively. I mean, in Angular 2, I'm sorry. In Angular 2, decorators are used extensively. So they're probably kind of a good thing to get used to. And I think they can end up being very powerful and kind of allow you to express JavaScript code to make it look more like Java or C# code, which may make some people more comfortable. Which I think is one of the goals of TypeScript, to make people more comfortable.
Is there any impact on performance as opposed to just the old-fashioned way of, like, for example, for your, I guess, for your example of the logging?
Right. So, I mean, like, this pattern, I mean, I haven't really measured it. I think there'll probably be some sort of minor impact because it's wrapping something in something. So there's obviously a little extra layer there, and if you have a closure, it's some extra memory. That's not the level we should be optimizing at. You optimize. So I mean, like to talk. So, I mean, optimizing code is kind of, you optimize based on measurements and not based on, that looks like it might not perform as well. And it's really, the goal of the combinators is kind of to enforce that single responsibility principle, to abstract logic that is common to a whole bunch of different functions, and is kind of separate from the work of the function. And you incur probably a little penalty, but time-wise, it's not a big deal, right? So you kind of need, and to kind of think about optimization, you need to figure out where your optimization problems are. I'm going to babble a little bit more because no one's like running for the door yet. You probably should, but so there's a very famous in vogue JavaScript framework right now called React, and what that does is Facebook went in and they analyzed why are JavaScript frameworks slow, and they determined the JavaScript framework is slow because of the DOM, the document object model, which is kind of the browser and the HTML. So what they did is they have code that generates an entire virtual DOM, right? And they instead of modifying the DOM, they modify this virtual DOM. And they have this whole process that compares their virtual DOM to the DOM to create the minimum set of changes required that can be batched in a very effective way to the DOM. So they built this whole thing that like does comparison on the DOM and built this whole virtual DOM because the optimization problem was modifying the DOM. So a lot of times, I mean, I think it's a good lesson because it points to the fact that sometimes what you think is going to be, optimal isn't, and you got to figure out where the actual problem is, right? And you wouldn't think that, oh, I need to create my own entirely, my own copy of the DOM and modify that and rebuild that. And the way they write the code is they rebuild it all constantly, then compare this rebuilt version to their old version, and that doesn't seem intuitively optimal, but it ends up being very fast because they've kind of figured out where the problem in performance is. I hope this was at least amusing. But thank you for listening to me rant.